a differential pair and its termination. This differential DDR4 clock signal starts at the controller. With very slight discrepancies at corners, the complementary signals travel together until they reach the first RAM. Then they fly by and continue with exact matching to the second RAM and the termination network that's placed on the opposite layer. As with single-ended signals, trace widths and nearby fixed voltage and ground planes affect the impedance seen by travelling waves. But in a pair like this, the two complementary sides couple electromagnetically, and that also affects the impedance. The odd mode impedance, where one side is rising as the other falls, as it should, is different from the even mode impedance, where both are rising or both are falling. This is called mode dependency. The more the two sides couple to each other, and the less they couple to power and ground planes, the more mode dependent the impedance becomes. To terminate the two sides of a differential pair separately at the far end, you usually use the odd mode impedance, like this. And the simplest termination between the two sides uses the differential impedance, which is exactly double the odd mode impedance. So, why does this real DDR4 termination look like this? The answer lies in that modality. It's designed to give the best possible result in an imperfect world, where there's noise and where even the signals could be fractionally out of alignment. Even a well-routed differential pair can pick up noise that propagates in a mode you don't want. There's a DC termination path between the two sides of the differential pair, and an AC termination path from each side through the capacitor to a fixed voltage, so that a sensitive differential signal like this can get from driver to receiver with as little unexpected distortion as possible.